Approximate query processing provides an excellent trade-off between query accuracy and latency for data analysis over large databases using random sampling. The existing AQP system that supports online transactional updates usually performs scan-based sampling, which is easy to implement but can also slow due to the linear scan cost. In this demonstration, we will show how to achieve a much faster response time in such system using index-assisted sampling over AB-tree, a recently developed concurrent index for sampling and online updates. We simulated an online business transactional database using TPCC with 100 warehouse and 100 million rows in the largest table initially. We image data analysis will issue ad hoc approximate queries in the database to gain real-time insights. The audience will act as one of the data analysis and compare the performance of different approaches. We will also set up a larger instance to demonstrate the scalability during the live demo. Now, let's turn to the front-end interface. This interface allows the audience to issue queries, adjust the background workload mix, and examine the system performance metrics. In the first panel, the audience can choose from the example queries. Once they select one of them, 3 versions of the same query will be automatically populated into the input boxes. For example, we can select Q1, which computes the total revenue of the sale up to the certain date. The audience will also be able to customize the query as they want. For example, they can change the cutoff date in Q1. When we click Run, the query will be sent to the Postgres background to execution. The first version of query is the exact query using full scan, which takes more than 10 seconds in the moderate-sized database. When Postgres finishes execution, we can find the query result and the running time below. As we can see, the query result fairly slow because of the costly full table scan about 100 million rows. The second query is an approximate version of Q1 that performs index-assisted sampling to obtain simple random sample with replacement. To achieve that, we develop a Postgres extension PGAQP, which provides a new table sample operator for simple random sampling with replacement, as well as the rewriting rules that transform approximate aggregation operators into unbiased estimators. The users will be able to customize the sample size during the live demo. Under the hood, PGAQP will select the index-assisted sampling access path for the SWR operator using the AB tree. Now, let's click Run. The result returns almost immediately within just around 100 milliseconds. This is because the sampling cost scales linearly to the sample size rather than the table size. The third is the same approximate query but with the Bernoulli sampling operator, which is scan-based sampling operator. We set the sampling percentage for Bernoulli so it also returns roughly 4,000 samples. PGAQP can also rewrite the approximate aggregation operators properly for Bernoulli sampling. As we can see, scan-based sampling is at least an order of magnitude slower than the index-assisted sampling in the database. This is because scan-based sampling has a linear cost to the table size. The larger database is, the larger will be the gap. We can also click the plot relative error to compare the errors for both approaches. As we can see, both achieve similar errors within the 5%. In the second panel, the audience can also set up a background workload with concurrent update and sampling. They can select from example workloads or customize the TPCC transaction mix as well as the background sampling threads, which simulates approximate queries from other data analysts. Let's start the workload and turn on the third panel to see the performance metrics. As shown in the graph, AB-tree can sustain very high insertions and sample throughput without impacting each other. We can also find other system metrics on the page, including CPU usage, memory usage, and I/O throughput of the system. Finally, let's go back to the ad hoc query panel and run our approximate query with index-assisted sampling again. As we can see here, the latency of the query is not impacted by the background workload, which involves heavy insertion. That shows we can achieve very low response time for approximate queries in a system under heavy concurrent updates.